Did you watch? This was Dr. Rafi. Welcome you. Who is from Dr. School of Economics. His area of specialization is international finance, macroeconomics, and applied economics. Now, Dr. Mohammed sir.
Thank you very much for your kind words. This is the second day of the workshop where in the last class, Sahad would have discussed about the need for the econometrics or, for the applied economic studies. Let me share my screen. Hope you can see my screen. All right. I'll be discussing today about the simple and multiple regression model using the ordinary least square method. So this is a very widely used method in econometrics, the ordinary least squares method. So I'll be explaining about the simple as well as the multiple regression model. Hope you know the distinction between the simple and multiple regression. So in case of the simple regression model, where we have two variables, we try to find out the relationship between two variables. Can you guys hear me? Hope all of you can hear me. Any participants?
Yes, sir, it is audible.
Okay. But in the background, there are some disturbance. If all of you can mute. Right. So I'll be talking about the simple and multiple regression model. In the simple regression model, we are talking about only two variables. You have a dependent variable as well as an independent variable. And we try to find out the relationship between these two variables. And in the multiple regression, you have more than two variables, where one dependent variable and more than one independent variable. So I'll be explaining about the ordinary least square method. How do we apply the ordinary least squares method to find out the or to go for the simple regression as well as the multiple regression. Now this is the outline of the presentation, where I'll start with what is the ordinary least squares. So the name itself indicates that it's a least squares. So we are going for a least square method. Least square of what? The least square of the error term. So we are, the ordinary least square method is being introduced by, minimizing the residual sum of square, or we are going for the lowest residual sum of the square. Then I'll be explaining the intuition, or I'll be explaining the logic for going for the least squares. Why do we go for the least squares? Or why do we minimize the residual sum of squares? Then I'll explain about how do we minimize the residual sum of squares. That is what exactly the ordinary least squares method is doing. Then I'll take up an example and I'll show you how do we find out the values, how do we find out the estimates of, say, the relationship between two variables. Then I'll explain about the statistical inference from that particular regression. And the same thing will be explaining about the multiple regression. We will explain, and I'll also take up an example and show you how do we go for the multiple regression, and we'll interpret how do we interpret the results. Now, let me begin with the simple regression model. So this simple regression model talks about, or it gives you the relationship between two variables. And you might have studied about the correlation, which also talks about the relationship between two variables. Now, in the correlation, you get whether they are moving together or not, whether they are moving in the same direction or not, and what is the extent of the relationship. But the correlation does not talk about whether the variations in one variable actually leads to the variations in the other variable or not, or whether the variation in one variable can be explained by the variations in the other variable. So the regression will help us to understand that. And here, apart from the correlation, we distinguish between the dependent variable and independent variable. And we see how the variation in the dependent variable can be explained by the variations in the independent variable. So I'll be using different terms for the dependent as well as the independent variables. I'll be using the explained or an explanatory variable, or the regressant and regressors throughout this lecture. So any of these words I'll be using. So the basic purpose is to understand how the dependent variable will change when there is a change in the independent variable. So we say that when there is a 1 unit increase in the independent variable, how much will be the increase or decrease in the dependent variable. Therefore, suppose we have two variables. Say y is the dependent variable and x is the independent variable. Then econometrically you write it as yi is equal to beta 0 plus beta 1 xi plus ui. So this is the econometric specification of the relationship between the dependent variable y and the independent variable x. And this is a linear relationship. We are talking about a linear relationship or linear regression model. Now, the last class I have discussed about why do you know what is the distinction between the econometric model and the mathematical model. So if you are writing the mathematical relationship between y and x, then you don't include the error there. So here in the econometric model, we give a space for the possibility of the error. And the whole process is that we try to minimize the error. Now, why do we include the error term in the regression or error term in the econometric model? So there are different reasons why we include. Because here we are talking about the relationship between two variables. The relationship between y and x. But there will be, say, suppose we are talking about the absolute income hypothesis. We are talking about the relationship between your current consumption and current income. So the Keynesian absolute income hypothesis says that the consumption depends upon the current income. So if you are going for a regression model where you are trying to find out the values of beta 0 and beta 1 here, that means you try to find out what is the value of the marginal propensity to consume. That means you try to find out when your income is increasing by 1 rupee, whether how much will be the increase in your income. How much will be the increase in the consumption. That is the marginal propensity to consume, the beta 1 value. And you can also find out the value of the autonomous consumption, that is beta 0. So we try to find out the relationship between these two variables, the consumption and income. Now, in that, there will be different variables which also leads to the changes in your consumption. Your wealth might be one variable which can explain the variation in your consumption, or there will be different other variables. Now we include the error term because of different reasons. So one reason is that we are not, there can be a chance that there is a omitted variables. You don't include different variables which can also explain the variation in the dependent variable. Say for example, in this case, if you have not included wealth, so that's an omitted variable. You are only talking about the relationship between the income and consumption. So, whatever the omitted variables can explain, that will be reflected in the form of the error term. And there are different reasons why you don't, include some of the variables. So one reason would be the vagueness of the theory. The theory might be explaining about only the relationship between the consumption and income. Or even if there are some theories which talks about the relationship between the consumption, income, and some other variables, say wealth. But if the data is not available for wealth, then you don't include that variable in the model. So this is another reason. And there will be some peripheral variables. By peripheral variables, I mean there are some variables which affect the dependent variable, but the extent of their impact might be very less compared to the main variable, the income, which we have included in the model. So you don't include, you consider them as the peripheral variables and you don't include them in the model. And there is a concept of the parsimony. You always, the econometricians always go for the parsimonious model. By parsimonious model, I mean the simplest model where you don't have to estimate too many parameters. So in that case, you omit different variables. So, the impact of those variables you have omitted in this regression model will be reflected in the form of the error. Because you may not be able to estimate the value of the dependent variable, which is as close as possible to the actual value. And another reason is the measurement error. You may not be including the actual variable which you are supposed to include. I'll give you an example where you talk about the permanent income hypothesis, which explains about the relationship between permanent consumption and permanent income. But you don't have data for the permanent income and permanent consumption. Instead, you are going for the actual income or actual consumption. So you are going for a proxy which actually does not fully represent your actual variable. In that case, say if you are going for the actual income and actual consumption, then what happens is there is a measurement error. So those things will be captured in the error. And another reason is that sometimes you might go for the wrong functional form. Suppose we are talking about a linear relationship where you have a dependent variable y and independent variable x. Or you might be talking about a linear logarithmic relationship where your dependent variable is in the usual form, but whereas your independent variable is in the logarithmic format. Or you can have a log-lim form where dependent variable is in the logarithmic format. Or there is a double log format where both the variables, the dependent as well as the independent variables, are being expressed in the logarithmic format. So there are different functional forms. And the interpretation also differs. In case of the the double log format, you explain that when there is 1% change in the dependent variable, what happens to the or how much will be the change in the dependent variable. You talk in terms of the elasticity, or you talk in terms of the percentage change. Suppose you are supposed to talk about the elasticity. you are supposed to talk, estimate the elasticity between y and x. But instead of going for the fourth model, if you are going for the first or second model, so this you are going for a wrong function. So in that case, the error term will capture that. Or you are supposed to go for an inverse function. You can consider the Phillips curve, which talks about the inverse relationship between the inflation and unemployment. So in case of the Phillips curve, you are supposed to estimate the inverse function, whereas you are going for the usual linear function. So in that case, this is an example of wrong function. So because of the possibility of these reasons, we do include the error term. And we explain the econometric model to find out the relationship between y and x as yi is equal to beta 0 plus beta 1 x plus 2i. Now, I'll give you an example of the income and consumption. So we would like to estimate the relationship between income and consumption. Suppose you have data for some 60 families. You have data on income and consumption, and you would like to estimate the autonomous consumption and the marginal propensity to consume, or the beta 0 and beta 1. Now, you can see that x is the independent variable, the family income, and y is the dependent variable. So there are 10 groups, you can see here, 10 different groups with a particular level of income and their consumption. Now, if you find the relationship, if you plot it like this, if you plot the relationship between the income and consumption, you are getting a positive upward slope, positive sloping curve. So this is what we would like to estimate. This is the line. This is the line which we would like to estimate, which will tell you about the relationship between consumption and income. And we are talking about a community where there is, the total population is 60 families. Now, this is an hypothetical example. So we are actually, our intention is to estimate the relationship between y and x, where you can see that this is the population regression function we would like to estimate. So we are actually trying to find out the value of beta 0 and beta 1, which is coming from the whole population. But in this hypothetical example, we have data from whole population, but that will not be the case always. So the usually we don't have data from for the whole population. Whereas what we do usually is you pick up a sample, you go for a random sample, and you go for applying the regression model. So what we would like to know about, the population relationship or the population regression function. Whereas we are actually going for a sample regression function. That means, from these 60 families, you are only going for, you collected some 10 families, the data on income and consumption for 10 families. Then you go for estimating the beta 0 and beta 1. Then this is a sample regression function. So we are going for a sample regression function, and we would like to infer about the population regression function. So we usually go for a sample regression, not the population regression. Now, if you plot this relationship, you can see that, again, we are actually here, you can see that we try to fit a line which is passing exactly through the middle of this scatter, which will tell you about the relationship between the dependent and. So, the whole point here is that we do not have the population, whereas we have the sample which can represent the population. Therefore, we are actually, what we are doing is that we would like to estimate the population regression function. whereas we are going for a sample regression function. So the aim is to get beta 0 and beta 1, whereas we are actually estimating the beta 0 cap. We are finding the beta 0 cap and beta 1 cap. That represent the sample regression function. And we infer about the population. So that is the whole process we are doing. Now, you can see that you can estimate. So, the first one is the sample regression, where if you estimate, you get the, you try to estimate a line which talks about the relations between the dependent and independent variable. So you estimate the values of beta 0 and beta 1 and fit a line which is passing exactly through the middle of the scatter plot, which talks about the relationship between x and y. Now, we would like to have our estimated value. We would like to have our estimated value as close as possible to the actual value, or it should represent the actual value. So we would like to reduce the error. The error is nothing but the actual value and the estimated value. So for each observation, say in the earlier example, we have 10 observations. For 10 observations, you have an actual value and you have an estimated value. This, we are trying to estimate this relationship. So the error term is nothing but the actual value minus the error. Minus the estimated value. And here, when the regression line is passing through the middle of your scatter plot, what happens is that you get different error terms. In the earlier example, you get 10 error terms. And if you take the sum of those error terms, if it is passing through the middle, then the sum of the error term, sum of the deviation of the actual value from its mean will be 0. Now, so our intention is to fit a line which is passing through the middle of the scatter plot, so that it can represent the population parameters. Now here, in this Excel, you can see that there is a data for two variables, x and y. X is the independent variable and y is the dependent variable. And you can see the plot of the relationship between these two variables. So these plots are actually the plot of x and y, the scatter plots, tell you about the relationship. Now, from this scatter plot, you know that this is an upward sloping going to get. Or this tells you that there is a positive relationship. You can see that when x is increasing, the y is also increasing. So on an average, you get a positive relationship, right? Now, our intention is to draw a line which is exactly passing through the middle of the scatter plot, so that y cap, the estimated value, will represent the whole data points, the actual data points. So the ordinary least square method is trying to fit a line which is exactly passing through the middle. What to do is that this, you can see a red line here, which is the fitted line. Find the fitted line. It is beta 0 cap plus beta 1 cap xi, right? Now, you can get the fitted line. You can estimate when you know about the values of beta 0 cap and beta 1 caps. Now, I give different values for the intercept and slope. So this is the intercept, means it's the beta 0 cap. And slope is nothing but beta 1 cap. So I give different values for beta 0 and beta 1. So we are trying to estimate the relation between y and x. the estimated value is equal to beta 0 cap plus beta 1 cap xi. So when I give some values for beta 0 and beta 1, you can estimate the dependent variable. This starts from somewhere here, and we know that this, the relationship is positive. So let me give some values. Let me give the intercept beta 0. So I'm going to estimate this relationship. I'm giving some values for beta 0 and beta 1. So now I'm trying to estimate, trying to explain what is the logic behind going for an ordinary least square method. Now let me give some values. For beta 0 cap and beta 1 cap. Now you can see that the estimated value, this is the estimated value. This is nothing but, the beta 0, the intercept plus slope multiplied by the independent variable. Now I have given intercept value 50 and slope coefficient 3. Now, this is too much away from the middle points. Now what I'm going to do is that let me increase the slope coefficient. Say I increased from 5 to 6, or let me increase to 7. Now you can see that the fitted line is moving towards the middle point, or let me increase the value of the intercept, or let me put it as 7. So this is moving or let me put it as 80. So this is moving very much close to the middle point. So when it is moving towards the middle point, or if it is exactly going through the middle point, you can see that you have the error terms. Error terms are nothing but the difference between the actual value minus the estimated value. So here you can find the error term, the difference between these two. Now, as I said, when you fit a line exactly through the middle, then the sum of the error terms will be equal to 0. Now what I'm going to do is that I'll find the sum of the errors. This is the residual. This is ui cap. That means the actual y minus the estimated value. The actual y minus the estimated value for all the data points, for all the 14 observations. And when you take the sum of those 14 points, you get the sum of the error term. Now we have seen that when it is going exactly through the middle of the scatter plot, then the error term will be 0. Suppose, let me give 4 here. Now this is away from the mean. That means you can see that the sum of the error term is increasing. Let me put this is equal to say 30. Again the error term is increasing. So as it is coming closer to the middle point, what happens is I can see that the error term is reducing. But still we have not reached a point which is going through the middle, because the sum of the error is not equal to 0. Now, so this, but still, you can see that this fitted line is almost representing the relationship between x and y, which is positive. So this line is upwards. Now, you just remember this number, the sum of the error term 184. Now what I'm going to do is that I'm going to draw another line, another fitted line, which passes through the middle of this relationship. But what I'm going to do is that I'll find out the average value. Of y. I'm finding out the average value of y, which will I just found out the average, the mean of y, mean of the dependent variable. Now what I'm going to do is that I'm giving this value. I'm giving this value for the intercept 145.643. Okay, and the slope, let me give as 0. Now you can see that this fitted line is going exactly through the middle, but and the residual, the sum of the residual is equal to 0. Now, when it, so we have two examples where we had an upward sloping curve and a straight line. So, which one is better? Which one is actually representing the relationship between x and y? The first one or this second one? Of course, not the second one, right? The second one actually, it's giving a straight line. Whereas from the scatter plot itself, you can understand that the x and y are positively related. Now, what I'm trying to say is that even if you are drawing a line which is passing exactly through the, which you are drawing by taking the average of the dependent variable, then you get a horizontal straight line, and which minimizes the sum of residual, So, the minimizing the sum of residual should not be the criteria to fit a line which represent the relationship between x and y. Now, we have seen in the earlier case that the sum of the error is not 0. But whereas we could see that this line represent better than the other one. This represents the relationship between x and y better. Now, this happens, you get, when you draw a straight line, you get, both positive and negative values. And when it cancels out, you get the sum of the error, which is equal to 0. Now, so you should not go for a method which minimizes the error. Then there should be some alternative method, right? Now, the problem here is that, suppose you are estimating the, you are fitting a line where you have both positive and negative. And when you add that, you get 0. Now, there is another, there is another method, or the ordinary least square method has been introduced by Carl Friedrich Gauss. So he tells that you don't go for minimizing, or you don't go for a method which actually gives you 0 sum of the error. He is in favor of going for the residual sum of square. So he tells that you minimize the residual sum of square. You calculate the error term, then you take the square of error term for each observation, then you take the sum of it. I'll explain you two cases, which will make you clear what is the need for going for the residual sum of squares. Now you take a case where the actual value is 100, whereas you predicted that it is 98. So the actual value is 100, but your predicted value is 98. That means the error, that is the actual minus the predicted value, is 2. And you make another prediction. You predict exactly 100, and the error is equal to 0. Now there is another case, the second case, where you predicted that the actual value, though that actual value is 100, you predicted that the estimated value will be 95. That means the error is 5. And in the second case, you predicted that it is 105. Again, the error is minus 5. So you have, in the second case, you have, 5 and minus 5. But you take the sum of it, what happens is that in the second case, the sum of the error will be 0. But in the first case, the sum of the error is 2. and you end up saying that the second model is better. But you know that the error is higher in case of the second model. Though you have the positive and negative errors. So you should penalize both negative and positive errors in the similar way. So one way is either you can go for taking the actual, the absolute value of the error, or you can square them. So if you square the error, you and take the sum of it, you get 4 in case of the first case, and in second case you get 50. That is 5 square plus minus 5 square. So if you are going for the square of the residual and taking the sum of it, then what happens is that you penalize both positive and negative errors. So this is the logic behind going for the residual sum of square. Now, you should not, go for minimizing the residual, whereas you should go for minimizing the residual sum of squares. That is what exactly the ordinary least square method explains. Now you can see in this example where if I give the this value, if I give 145, you can see that the residual sum of square is the residual sum of square. How am I calculating the residual sum of square? You have the actual value y here, you have the predicted y, then you take the deviation. This is nothing but the actual value minus the predicted value. The predicted value you calculate as your beta 0 plus beta 1 multiplied by xi. So you calculate the error and you take the square of each errors. And you take the sum of those errors. That is sigma ui square. Now you can see that when you give the intercept 145, you get 33,247 as the residual sum of square. But whereas, let me give the other values, 80 as the intercept and 7 as the slope. Now you can see that the residual sum of square is lesser. It is 22,000 something. Now we are actually trying to reduce the residual sum of square. Suppose let me put it as say 7.5. Now again the residual sum of square have reduced. Now let me put it as maybe 85. Now you can see that the residual sum of square is reducing as when this the fitted line is almost passing through the middle. So the whole process is that we try to reduce the residual sum of square rather than reducing the sum of the residuals. So this is the whole process we are trying to do in case of and we don't know which is the minimum residual sum of square. So what you can do is you can give different values here and estimate the residual sum of square. Now what I did is I have created a table where I have given different values for the slope and intercept. So this column represents the intercept and the row represents the slope coefficient. Now let me give both 0. Let me give both 0, then you can see that the residual sum of square is 3,30,207. That is what this one. Suppose I'm giving say 40 as the slope coefficient, 40 as the intercept and 0 slope coefficient, then I'll get 1,89,487. So let me give 40 as the intercept and 1,89,000. So this table is being created by giving different values for intercept and slope. Then you can calculate the residual sum of square. So these are various residual sum of square being calculated by giving different values. Now you get the best fit line when the residual sum of square is minimum. Now, what I'll do, I'll see the minimum out of this whole table, where I had given a different number. I had given different number. So what I'll do, I'll find out the minimum. I'll find out the minimum from this table. Minimum residual sum of square. So the minimum residual sum of square is 20,245, which comes here. Then the intercept is 88.956 and the slope coefficient is 7.558. Now you can see that when you give that value, the 88.956 and 7.558. 88.956 and 7.556. So you can see that you get that. This is the minimum residual sum of square. But here actually we are giving different values for beta 0 and beta 1. Now this is a laborious process. Now, if you can do ulta, if you can find a value for beta 0 and beta 1, which is actually minimizing the residual sum of square, then you get the best fit line. Now what I'm going to do is that I'll go for the solver where I try to minimize the residual sum of square. So what I do in Excel, you can see that there is an option called solver, which go for either maximization or minimization. So here, we are trying to minimize the residual sum of squares. So if you do not have in your Excel, you can go to File and here there is the last options where you can go for add-ins, and there is in add-ins there is a tool called solver. So you can see that the solver is being added in my list. So if it is not there, you can add. So what I'm going to do is that I'll minimize the residual sum of square and find out the values of beta 0 and beta 1. So what I'll go for minimization. You have different options. Either you can maximize a column or you can minimize a column, and you can set the value is equal to something. So here we are going for minimizing the residual sum of squares. That means we are minimizing this column. We are trying to minimize this column with a condition that you can change the values of these two and find out the best values. Now if you do that, you can see that the intercept is 88.96 and slope is 7.558. So what we actually do is that we minimize the residual sum of square so that we get the beta 0 and beta 1, which exactly fit the relationship between x and y. So this is the logic. This is the logic for applying the ordinary least square method, because the ordinary least square method is also doing the same thing, which actually tries to reduce or minimize the residual sum of square and calculate the value of beta 0 cap and beta. Hope all of you have understood the logic behind going for minimizing the residual sum of square. Now, as I said, Carl Friedrich Gauss has introduced the ordinary least squares method, which actually tries to reduce the residual sum of square. Now, you have the actual value and you have the estimated value and the error term. So you have error term for all the 14 observations in this case. You square them and you take the sum of the square of the residual. So when you take the square of the residual, this is nothing but you deduct yi cap from y, that is ui, Then you take the square of it for all the observations, all the 14 observations here, and take the sum of it. Now, the ordinary least square method is being introduced by minimizing the residual sum of square. So, this is a problem of optimization. So, we apply the theory of optimization here. And you try to minimize. How do you go for minimization? So, we go for the first order condition, right? You take the differentiation, you take the first order difference of sigma u I cap square with respect to beta 0 cap and beta 1 cap. Then you equate with 0. That is the first order condition. Then you can derive the actual values of beta 0 cap and beta 1. So we are going for the minimization where we apply the theory of optimization. You take the first order difference. So we are actually, minimizing the residual sum of square with respect to beta 0 cap and beta 1 cap. So what we actually do is, this is a two-step procedure. In the first step, you find out the first order difference. You find out go for the differentiation with respect to beta 0 cap and beta 1 cap and equate with 0. This is the first order condition. So from that you will get two normal equations. Two equations you will get, we call it as normal equations. Then when you solve those two normal equations, you get the value of beta 0 cap and beta 1 cap, which actually minimizes the residual sum of squares. Now, what we do is we minimize with respect to, you differentiate it with respect to beta 0 first. So you can write, here what we are actually doing is we apply a chain rule and minimize the, you take the first order difference of the residual sum of square with respect to beta 0 cap. I'm not taking much time on these equations. So when you, go for this differentiation, you get a normal equation. So you get the first normal equation when you differentiate the residual sum of squares with respect to beta 0 cap. And then you take the, differentiation of RSS with respect to beta 1. Again, here we are going for the chain rule of differentiation and you get the second normal equation. So we have two normal equations here. We have two normal equations. And then you solve these two normal equations. If you solve the first normal equation, you are dividing the entire equation by n, then you get the beta 0 cap. So we are actually taking the differentiation, going for the differentiation with respect to beta 0, and we got the first normal equation. When we solve it, you get beta 0 cap, which is equal to y bar minus beta 1 cap x bar. And you take the second normal equation, and instead of beta 0 cap, you expand that in this equation, then you get the value of beta 1 cap, which is equal to sigma yi xi minus n x bar y bar divided by sigma xi square minus n x bar square. Now, you would have, seen another equation for the beta, the slope coefficient. That is sigma xi yi divided by sigma xi square. So this xi, it is the deviation of actual value from its mean. Yi minus y bar, we are writing as small xi. So you can go for, these two equations. The beta 1 you can apply, you can estimate the value of beta 1 using these two equations. Both are similar. Here you can see that, when we expand the numerator, you can see that the numerator in both these equations are same. And when you expand the denominator, this is also same. So, you can, what we are actually, the ordinary least square method is doing, which is trying to minimize the residual sum of square with respect to beta 0 and beta 1 cap, which will give you the best f line. So you can apply, these two equations. You can find the value of beta as 1 cap, which is equal to sigma x I y I. This x and y are the deviation of actual value from its mean divided by the sigma xi square. And beta 0 cap also you can find out using these equations. Now, this will give you the best fit line. So what I'll do, I'll use these equations to find out the value of beta 0 cap and beta 1 cap. So here we have, this is the independent variable x and this is the dependent variable y. So when you go for this equation, you can estimate the value of beta 1 cap, which is sigma xi yi divided by sigma xi square. So what we need to estimate first is to find out is x, small x, which is equal to the x minus x bar. So you have the x bar is the average value of x. So we find out the average of this and take the deviation. In the similar way, we find out the average value of y. Now, you can find out the small x, you can find out the small y, which is nothing but y minus y bar, and you need to have x y, and you need to have x square. You need to have x square. So this, the equation says that in the numerator you have sigma xi yi, and in the denominator you have sigma xi square. Now, you can find out the value of small x, which is the actual value minus the mean value. So what I'm going to do is that I'm finding out the deviation of actual value from its mean for both x and y. So let me first find out for x. Now, what I'm going to do is I'm giving a dollar sign here. I'm giving a dollar sign here so that, the mean value, the average value, that cell remains same, even if you are scrolling down. Now here you can see that, all these values gives you actual x minus x bar. You can see that, the cell which represents x bar doesn't change. Now, in the same way, you can also calculate the value of y minus y bar. Let me put a dollar sign here so that the cell doesn't move. Now you have the small x, small y, and the equation says that you need to multiply them and take the sum. Now, you multiply both x and y. You get xy, and if you take the sum of xy, what you get is the sigma xy. That is what the numerator for calculating the beta 1. So beta 1 is nothing but the slope of this line. And you need xi square. You can find out the value of xi square. So what I'm going to do is that I'm taking the square of x. So you can see that this is the different values which is giving you the xi square. And when you take the sum of xi, or values from 1 to 14, you get sigma xi square. So what we need is sigma xi yi and sigma xi square, which will give you the slope coefficient. Now here you can calculate the beta 1, which is equal to sigma xi yi divided by sigma xi square, 7.558. That is what we got in the earlier case, right? After so much calculations. And you can find out the value of beta 0 cap, which is y bar minus beta 1 cap x bar. So y bar is the average of y, x bar is the average of x. So you get beta 0, which is equal to y bar minus beta 1 multiplied by x bar. Right, that's the equation. So, the equation says that y bar minus beta 1 cap x bar. So, you can find the value of beta 0. So, this is how, the ordinary least square method has actually made the life easy, which has given you two equations, which will give you the minimum residual sum of squares. So, that which represent the relationship between x and y. Now, this is the way you manually do. But now we have softwares available. Even in Excel, you can do, you can find out the values of beta 0 cap and beta 1, which tells you about the actual relationship between x and y. Now, there are different ways. You can do the regression. Now, I'll explain two ways in which you can go for regression in Excel. So you have the x variable, the independent variable, and you have the y variable, which is dependent variable. Now, what do? You go for the scatter plot. You go for the scatter plot of these two. Now, here you can see that what you have on the horizontal axis is x, and on the vertical axis you have y. Now, our interest is to fit a line which exactly goes through the middle and find out the values of beta 0 cap and beta 1 cap. Now, what you can do, you select all these points together, and you can go for right button, click right button, and there is add trend line. If you go for that, this will ask you, there are different ways you can draw a trend line, but we are going for a linear trend line. And if you want to display this equation so that you get the value of beta 0 cap and beta 1 cap, so there is an option, display equation on chart. If you click that, what you get is the regression level. So here you can see the values of beta 0 and beta 1. And this is one way you can calculate the values of beta 0 and beta 1. Or you can also, there is an option in data where you can go for data analysis. Again, this is, if this is not activated, you can go to add-ins and include, if this add-in is not activated. So if you want to find out the relationship between x and y, if you want to go for the simple regression model, you can go to data analysis and regression. Okay, so this will ask you the input y range, that is, which is your y variable, the dependent variable, and the input x range. Input x range means the independent variable. So you can select the independent variable here. Now, you note one thing, that we have also selected the label. We have also selected the name of the, we started with first one. So in that case, you can select this label, and they will ask you, where do you want the output range? Let me put it here. Let me put the output from this regression here. If I click here, I get the regression result, where you can see that the intercept and slope coefficients are here. Now, this is how you get the result from a simple regression model, where you have a dependent variable y and independent variable x, and you have also included an intercept. Now, you get many other parameters along with these two. You get many other you get many other inferences. So how do we interpret? How do we interpret this result? So this says that you can look at various statistics. You have the standard error, you have the p statistics, and you have the p value, the probability value. Now, you might have seen in some papers that they report all of these three: the standard error, the t statistics, and p values. But all of them are telling the same story. They are checking whether the estimated coefficients, the beta 0 and beta 1 cap, are significant or not. Here, we are going for the hypothesis testing. So in this, the hypothesis testing, where you have an acceptance region and a rejection region, right? And if the value, if it is in the rejection region, you reject the null hypothesis. Now here, the null hypothesis is that the intercept value is equal to 0. That is, beta 0 cap is equal to 0. And beta 1 cap is also equal to 0. Using the t statistics or the p values, whether you have to accept the null hypothesis or whether you have to reject the null hypothesis, or you have to you accept the null hypothesis, or you fail to reject the null hypothesis. Now, this t statistics is, you can calculate the t statistics. This is the coefficient divided by the standard error. So the t statistics is, the coefficient divided by the standard error. So you can calculate, this from this table itself. You can see that the t statistics and standard error. So you don't need to report both. And at the same time, the p values are being calculated from the t statistics. So if you are looking at the 5% significance level, if your p value is less than 0.05, then you reject the null hypothesis, because that is in the rejection region. So if you plot this in the distribution table, then the p value, if it is less than 0.05, then it is in the rejection region. You reject the null hypothesis. So here the null hypothesis is that beta 0 is equal to 0 and beta 1 is equal to 0. So in both the cases, we say that we reject the null hypothesis and we accept that both of these coefficients are different from 0. So you accept these values. So here you interpret that you can interpret that when x is increasing by 1 unit, the y will increase by 7.56 units. Say both of them are in terms of rupees. You can interpret that if x is increasing by 1 rupee, y will increase by 7.56 rupees. So this is how you interpret. And you also get the r square. The r square will tell you about the how much of the variation in y can be explained by the variations in the independent variable. So here r square, you can see that it is 0.39. So almost 40% of the variation in dependent variable can be explained by your model, by Ex. So I'll take some time to discuss about the R square, or the goodness of fit. So the goodness of fit of a regression, that is the coefficient of determination, the R square will help you to find the proportion of the variation in the dependent variable, which can be explained by the independent variable. Now I'll give you a plot where you can see that each circle here, You have a circle for y and circle for x. So which says that the variation in y. So the circle for y is the variation in y, and the circle for x is the variation in x. So you have 6 figures where in the first one you can see that in figure A, both of them are staying independent. But in case of B, you can see that the variation in y is being explained by this gray area. And as you move from A to F, you can see that the variation in y, which can be explained by variation in x, is increasing. And in case of the first one, it is 0, and in case of the last one, which is 1. So the change in y is completely explained by the change in the variation in x. So this, you are actually trying to find out the R square, which is, which tells about this gray area. So the range of the R square will be between 0 and 1. Either it explains, the complete variation in the dependent variable, or it explains, it doesn't explain the variation, or you get in between 0 and 1. Now, so here you can see in this plot, you can see that you have a value for y and you have a value for x. The x is given on in the x-axis, the horizontal axis, and y on the vertical axis. Here you can see that the sample regression function is an upward sloping curve, where suppose the average y is given as the horizontal line, y bar. If at a particular point, the y is represented by yi, so the total deviation of y from its mean is given as yi minus y bar. So that is the total deviation. That total deviation you can split into two. Either explained by this regression, that is the deviation of the deviation of yi cap, the estimated y from the mean, and the error term. So either the sum of the deviation of actual value from its mean can be split into either as error term or explained by the regression model. So you can write this as the y minus y bar is equal to y cap minus y bar plus the error term. Now, as we explained, we are talking about the residual sum of square. We take the square so that the error term doesn't get matched with positive and negative. So here what we are doing is that you take the square of the deviation of actual value from its mean, take the square of the deviation of the estimated value from its mean, and the error term, the square of the error term. So the total variation in the actual value can be explained by either the deviation of estimated value or the error term. So you can write it in terms of the residual sum of square. The square of the error, if you take the sum of it, it's the residual sum of square. Or this you can write as the explained sum of square. How much is being explained by the model? And this is the total sum of square. So the total sum of square can be split into the explained sum of square and residual sum of square. So you can, so the total variation, if you split into two, you can write it as, the variation because of the explained sum of square and because of the residual sum of square. So what I'm doing is that, the total will be equal to 1. So the R square explains how much this model can explain. That is the explained sum of square divided by the total sum of square. Or the sigma yi cap minus y bar square divided by sigma yi minus yi. Or you can also write it as it is 1 minus the RSS divided by ESS. Or you can write it as 1 minus sigma ui cap square divided by the total sum of square. So you can calculate it, using either of these equations. Now that is how you calculate the R square. So I'm not going for the calculation of the R square, where the regression result will give you how much of the variation in y can be explained by Ex by through the R square. Now I'll spend some time to discuss about the multiple regression model. So here the logic is same, where we would like to go for a population regression and estimate the value, find out the value of beta 0, beta 1 and beta 2. Here you can see that the multiple regression model, you have more than 2 independent variables. Sorry, more than 2 variables, where you have more than 1 independent. So we know that one variable may not be able to explain the variation in the other variable, in the dependent variable. So you need to include, even in our example where we talk about the relationship, we talk about the consumption function, where various other factors, in reality various other factors will be affecting the variation in consumption. There will be wealth or the region where you are staying, there will be many factors which affect. So you have to go for the population, you have to go for the multiple regression model. Now here I'm explaining the multiple regression model where we have 2 explanatory variables. We have 2 independent variables and 1 dependent. So here we go for the sample regression function because we have a sample. We do not have the data on the entire population. And the aim is to estimate beta, find out the values of beta 0 and beta 1, whereas we estimate beta 0 cap and beta 1 cap. Again, we use the same logic. We minimize the residual sum of square. The ordinary least square method is being introduced by minimizing the residual sum of square. So what we do is that we find out the residual sum of square and you differentiate it with respect to beta 0, beta 1 and beta 2 cap. Then you get 3 normal equations. So when you have 3, differentiate the residual sum of square with beta 0 cap, beta 1 cap and beta 2 cap, you get 3 normal equations. And when you solve those normal equations, you can find out the values of beta 0 cap, beta 1 cap and beta 2 cap. Now, the beta 0 cap can be find out by y bar minus beta 1 cap x 1 bar. X1 is the first independent variable and beta 2 minus beta 2 cap x2 bar. In the same way, you can also find out the value of beta 1 cap. So this equation, you need to have the values of small y, small x1 and small x2 and the square of those values. Then you can find out the values of beta 1 cap. Similarly, you can find out the values of beta 2 cap. So these are the equations which is being derived from these normal equations. And these normal equations we get by taking you go for the differentiation of the residual sum of square. That is, you take the error term, you take the square of the error term for all the observations and sum all of those observations. So again, here we are using the same logic. We are going for differentiating with respect to each parameters. Then we are going for the first order condition. We are equating with 0 and we get the normal equations. And by solving these normal equations, you get the values of beta 0 cap, beta 1 cap and beta 2 cap. Now, you can I'll take an example. I'll take an example and go for the multiple regression model. But before that, I'll explain about the R square. So R square again explains about the variation in the dependent variable, which can be explained by the independent variable. Now, I'll go for the multiple regression where we have three variables. So this is the actual data from 20 Indian states. So we are trying to estimate the relationship between the total factor productivity and the other variables. So here our purpose is to find what are the variables which leads to the change in the total factor, the total fertility rate. So the TFR is the total fertility rate. And you have the female literacy rate. So in the literature, you can see, one of the variables which actually helps to explain about the fertility rate is female literacy rate, and the poverty, and the urbanization. So what I'm going to do is that I'm here going for a three variable model where we have one dependent and one independent. I'm not considering the urbanization here. Whereas I'll go for the multiple regression model. So since it takes too much time to find out the values of beta 1 cap and beta 2 cap manually, I'll use the data analysis portion. And here one thing is that since we have more than two independent variables, you cannot use the go for the usual scatter plot where you have to go for a three-dimensional diagram. So what I'll do is I'll go to data analysis, and you can find out the values of beta 0, beta 1 and beta 2 cap. So the input Y range is the dependent variable, the total fertility rate. And the independent variables, you can select these two. I'm going for a three variable model. So I'm selecting two independent variables, female literacy rate and the poverty. So we are going to check how, when the female literacy rate is increasing, what happens to the fertility rate. And when the poverty is increasing, what happens to the fertility, whether they are related or not. Now, you can select the labels and I'll put here. Okay. Now this will give us the result from the multiple regression model. So here you get these coefficients. You can look at the p-values. You can look at the p-values. So this says that the intercept is significant and the female literacy rate is also significant, whereas poverty is not significant. So this is greater than 0.05. So you fail to reject the null hypothesis. The null hypothesis is that these coefficients are equal to 0. So here you can interpret that when female literacy rate is increasing by 1 percentage points, then the fertility rate is reducing by 0.04%. So here you can and this is not significant. So this is how you can interpret, or you can look at the T statistics. Usually when the T statistics is greater than 1.96, the p value will be equal to or it will be less than 0.05. So when you can look at the T statistics, or you can look at the standard error and interpret the results. So here there is a slight difference in the interpretation. These coefficients are the partial coefficients. So this talks about when other things remaining the same, when all the other factors remains constant, and when the female literacy rate is increasing by 1 unit, the fertility rate will reduce by 0.034 unit. This is how you need to know that. So these are the partial coefficients. Now, there is one problem. You can look at the R square. You can look at the R square here. R square is very high. And we can also include the other variables. What I'll do, I'll take up the same dependent variable, whereas I'll include one more variable, the urbanization, to see whether the dependent variable can be explained better. Now here you can see that there are three independent variables. You can interpret using the p-value, that is statistic. And now you look at the R square. R square has improved. That means the R square has improved, and this says that when you include one more variable, the estimated value is coming closer to the actual value. So this is one problem when you go for multiple regression model. The R square will increase as you increase more variables, because you are actually including some more information in your model, so that the error term will reduce. So the R square, how do you find the R square? You find the R square by the 1 minus RSS divided by TSS. So what happens is, as you increase more variables, the RSS will come down, or the explained sum of square will be increasing. Therefore, there is another value which you can look at, is the adjusted R square. Because as you increase the number of variables, the R square has a tendency to increase. Therefore, the adjusted R square will adjust for the degrees of freedom, because as you increase the number of parameters, the degrees of freedom will be lost. The degrees of freedom, I mean the number of observations minus the number of parameters. So the degrees of freedom will be lost when you increase the number of variables. So here adjusted R square adjusts for the degrees of freedom. So which is being calculated as the adjusted R square, which you can calculate as 1 minus R square. This is R square is the residual 1 minus, R square is 1 minus RSS divided by TSS. So you can calculate the adjusted R square from R square in this way. 1 minus R square multiplied by n minus 1 divided by n minus k. So here in the adjusted R square, we are adjusting for the degrees of freedom. So in case of the multiple regression model, the adjusted R square is a better measure. So here you can see in the first case, the adjusted R square is 0.59. And in the second case, the adjusted R square is 0.58. So you can compare two models using the R square, and if it is a multiple regression model, you can compare using the adjusted R square, which adjusts for the degrees of freedom. So the adjusted R square you calculate using this equation: 1 minus R square n minus 1 divided by n minus k. That way you can calculate. So in the first case, where we have two independent variables, you can calculate this as, which is equal to 1 minus R square. You have the R square value multiplied by n minus 1 divided by n minus k. N here is 20. We have data from 20 states. So n minus 1 is 19 divided by n minus k. K is the number of parameters. K is the number of parameters including the interceptor. So here we have included two independent variables and one intercept. So n minus k is 20 minus 3, 70. Now, see, this is the adjusted R square. So you get the adjusted R square using this formula. So you can compare in the same way you can calculate from this table as well. So here, when you go for the regression, you look at certain parameters. You look at the coefficient values first, significant or no. If they are significant, you interpret whether they are positively related or negatively related. It is increasing what happens to the dependent variable. So either you can report standard error or you can report T statistics or P values. And in some papers you can see that in the parentheses they will give the standard error. Some star, 1 star or 2 star or 3 star to represent whether this is significant at 1% or 5% or 10%. Also you can interpret. So that will give you the standard error, and from that standard error and coefficient value you can calculate the T statistics. So in a way you can say that they are reporting all the statistics. And another thing you need to look at is the R square and adjusted R square. So the R, when you want to compare two models, you look at the R square or adjusted R square. About the simple regression model, where we talk about the two variables, the one dependent variable and another independent variable. And in case of the multiple regression model, we talk about the relationship among variables. You have one dependent and different independent variables, more than one independent. So we have explained about the ordinary least square method, which helps us to, it's a widely used method, which helps us to find out the values of beta 0 cap and beta 1 cap, which talks about the relationship between these two variables. Or in case of the multiple regression, which talks about the relationship among different variables. So this is one method. The ordinary least square is one method, and which is a widely used method. You have other methods such as the maximum likelihood method or GMM, generalized method of moments. Now, this ordinary least square method is being introduced with certain assumptions. So you have different assumptions, which is being introduced to explain the ordinary least square method. And when you follow all those assumptions, there are some properties. There are you might have heard about the Gauss-Markov theorem, which talks about the blue property. Best linear unbiased estimate. So when you use OLS, when you satisfy all the assumptions, it gives you blue. The properties of these parameters, the blue properties. So that will be explained in the next class by Harsh. So I'll wind up here. Thank you. I took exactly 1 hour and 30 minutes. So now if there are any questions, I'll take it up. So I hope you understood the logic behind going for the, minimizing the residual sum of square and how it gives you the actual, the estimated value, which is as close as possible to the actual values.
Sir?
Yeah.
Put some coefficient have some star in there, put some star on there. What is the reason for that? What is the base for putting the star?
No, see, we would like to know in the research papers, you can see that you have to tell about whether one variable is significant or not, one coefficient is significant or not. And if you want to talk about whether it is significant at 1% level or 5% level or 10% level, say here you can see that these coefficients, you can look at the p-value. If the p-value is less than 0.01, you say that this coefficient is significant at 1% level. If it is less than 0.05, you can say that it's significant at 5% level. And if it is less than 0.1, you say that it is significant at 10%. Now, in papers, you can see that to represent that, they put 1 star for, say, 10% significance, 2 stars for 5%, and 1 star, 3 stars for 1%. To say that whether this variable is significant. Is it clear?
Yeah, okay, sir. So one more doubt, sir.
Yeah.
You are told about the dependent values. Uh, the significance depend upon the x value and x value. What happen if the value about the intercept?
See, the intercept value, if you take the example of consumption income relationship, which talks about, you estimating the absolute income hypothesis, where you have consumption as the dependent variable and income as the independent variable. Now, in that case, the intercept will tell you when your income is 0, how much is the average consumption. So the intercept will tells that the autonomous consumption. Even if your income is 0, you need to consume, right? So the intercept will tell you about the autonomous consumption in this example, or if the explanatory variable is 0, what is the average dependent variable? But in all the cases, you may not be able to interpret in this way. You may not be able to interpret the intercept. So sometimes it makes sense to interpret. So it all depends upon which theory you are talking about. Is it clear?
Okay, sir.
Any other questions to take up? The chat box, I don't see any questions. See, I didn't take much time to talk about his derivations because that you can see in any standard textbook. So I wanted to explain about the logic behind going for the residual sum of squares. Vinegar sir, should we wind up now?
Yes, sir. Yes, sir. Yes, sir.
Okay, thank you.
Sir, thank you, sir. Now I invite Dr. Ashok Kumar to propose vote of thanks to the resource person and participants.
Thank you very much, sir. Today we have a very good session with the resource person Muhammad Rafi sir. Sir, really we have learned many things. You have give simple examples, and the calculation using Excel is very useful one, sir. I think participants will definitely will gain their knowledge on the econometrics using Excel. So it is a very good session, sir, and I thank you very much for your valuable session, sir. After that, I must thank the participants who have participated till from the 3:30 to now itself. Now up to 5, there no one left from the meeting due to they have enjoyed the session, I think so. Thank you very much, sir. For the participants, we have posted the feedback form. You please fill the form. After that, you can left from the meeting. Thank you very much.
Thank you, sir. Thank you, Ravik, sir.
Thank you for giving me such an opportunity.
Thank you, sir. Thank you.
Thank you. Bye.